Hello, everyone. Gonna wait just 1 minute for everybody to join. Thank you for being there. Hello. Hello, everyone. I prepared a little mate. I'm in Argentina right now for the DevConnect conference. Okay, we're gonna slowly start. Today, I'm gonna share a little presentation with you because today is going to be the number 3 of our community flashes. Every week, we're gonna be running a little community flash on every Tuesday, trying to give you the latest news and the details on how this Gossip project of a new generation of decentralized messaging private app is going. And today, the focus will be on the technology. So today, I'm going to show you exactly how it works inside. It's going to be a bit technical, so don't worry if you don't understand everything. But I think it's going to please quite a few of the technical people. And I'm also eager to hear your feedback if you have anything to say, if there's any issues that you see. I'm going to present a bit the technical parts, how it works, how it's built, why, and I'll gather all your questions. Of course, it's going to be not obvious to everyone how things work because it's a bit technical, but you'll have time to read the scientific paper because we just finished writing the scientific paper for for Gossip, and you can check it on our website usegossip.com. You can download it and read it calmly, and feel free to get back with more questions. But today I'm going to give a general introductions that's going to help you read this paper, and for the more scientific among you to be able to comment it, to deeply understand it, and to feel the innovation that's behind it. So let's start. I'm going to share my screen. Okay. So as a quick introduction, I don't know, do you see my screen? I'm not sure. Just a second. Just give me a second. This seems to be an issue with the screen share. Okay, I think it should be better. Let me just double check. Okay. Just 1 second. Yes, okay. So now it should be okay for everyone. Sorry for this little mishap. I'm not sure what happened. So here I'm gonna do a quick intro as a reminder on why we are building what we are building. So today there are quite a few so-called private messaging apps. We think of Signal, we think of Telegram, this kind of stuff. The issue is that almost all of them, if not all, they have some issues. Typically, they leak metadata, so the central server can know who is talking to whom, typically which phone number is talking to whom. They have metadata on when each person sends a message to each person, what's the size of the message, etc., etc. All this is kind of known by the server. and it relies on centralized infrastructure. And this is a subject of censorship. And actually, it goes even beyond. Even if the server cannot read the contents of the message, it has enough metadata to do a lot of stuff. And here's a quote of the former CIA director saying that literally, proudly, we kill people based on metadata. And that's a big issue. So here is a little screenshot as well on countries that have blocked or formerly blocked Signal or Telegram. Here's Telegram in particular. And on the right here is a list of messaging and other apps that died when AWS fell down. And this shows that all these companies basically depend on central servers on AWS, including Signal. You see it here. So this is an issue for us, and that's what we're trying to solve. This is what I presented last time already. So we're trying to create a messaging app that is end-to-end encrypted by default, that does not require a phone number, that has a decentralized backend, and that has sealed metadata. And as a reminder, to achieve privacy, resilience, censorship resistant, and safety, we need to log in without a phone number. We need the software itself to be hosted on decentralized platforms, so that you don't need to necessarily go through app stores. So if the system is censored on app stores, you can still use it. That's why we're going to use Massa's DWeb. No backend, peer-to-peer gossip only, sealed metadata. We saw that metadata is a big deal, and most of the censorship-resistant apps actually don't seal metadata. We want to be post-quantum because we saw that quantum computers are advancing quickly, and maybe there's a risk the existing cryptography might be broken. So we want post-quantum encryption. And we want also something that's really cool. It's plausible deniability, which means that even if I converse with someone and that someone decides to publish our conversation or to send it to the authorities, I can deny that I ever wrote any of it, because the system is designed in the way that the person I'm talking with can forge our conversation. It's on purpose, so that I can deny I ever wrote any of the messages. So the way it works is that to be decentralized, we're using a gossip network layer. We're thinking of actually piggybacking directly on Massa's network gossip layer. And the way it works is that if Alice wants to send a message to Bob, she encrypts a message, sends it to one of the nodes of the network, and the nodes of the network propagates the message to all other nodes through gossip, a bit like Bitcoin or Massa propagate transactions nowadays. And in the end, Bob receives queries the message from one of the nodes and receives the encrypted message, and there Bob can decrypt the message. That way, you don't even need to use something like Tor, because you already have a multi-hop gossip network here, and nobody knows who sent a message to whom. Node 1 only knows that this IP address sent some message, some encrypted message. They don't know to whom, and they don't know how exactly. And this node 4 node that Bob queried some encrypted message, and that's it. Of course, if node 1, 2, and 4 decide to talk to each other, well, then you have the same issue as in the Tor network, which is that node 1, 2, and 4, if they talk to each other and they gather and they say, okay, give me all your ciphertext, explain to me all the history of what happened, then node 1, 2, and 4 can deduce which IP address talked to which other IP address, but they still don't know the contents of the messages. So this is kind of interesting. And if on top of it, people use Tor to access the system, then we have something that's reasonably complete and that should solve the problem that we have. So as you can see, we don't rely on the central service. So if one of the nodes is malicious, if one of the nodes is down, it's still going to work. We are not the center of the system. Even if we disappear, it still works. Then comes the question of the phone numbers. You know that in Telegram, in Signal, you need to use your phone number to log in, or to pay some kind of extra service on Telegram that doesn't require a phone number, but then Telegram is not end-to-end encrypted by default. So it's a lot of caveats there. We're trying to solve this by using a central passphrase that's either chosen by the person that uses the device or that is generated on the device, that deduces an ephemeral root secret from which a key derivation function is used to generate a whole bunch of key pairs, a Massa key pair, a public key and a secret key for signatures. MLKEM secret public key pair, which is basically for key exchange in the context of post-quantum encryption, and ML DSA, so that's for post-quantum signature as well. And when you hash the public keys together, you obtain the user ID that is the pseudonym that the user is using inside the system. Of course, the user can anytime change identities, generate a new root secret, and obtain a new user ID. But that user ID is how people will connect to you to talk to you. That's what they need to know to send you a message. So for this to work, in the gossip layer, in the decentralized network, the nodes propagate messages, but they also temporarily store them for 2 weeks. And they index them by 3 possible indexes. They have a counter-based index for messages that allows user to query basically the latest messages that they have not seen based on the counter. Every time a new message is posted, this counter increases by 1, and basically Bob can query the latest counter-indexed cache. And this is used for announcements only for when, let's say, Alice wants to establish a new chat session with Bob. Afterwards, all the messages don't go through this cache. They go through a second type of cache, which is a public key indexed signed cache that is just a cache that's indexed by some public key, and the contents that are published are signed with the secret key associated with that public key. So this is used only to make sure that there cannot be any kind of front running, people stealing the slot of a message. They need to know the private key associated. And these public keys and private keys are ephemeral. Only the 2 members of the conversation know them, and at every message they change. So it's not like some kind of constant thing. It's ephemeral, and the 2 participants of a conversation at every message have a new one. That allows them at every message to publish the next secret key, at which the other participant of the conversation can seek the next message. And nobody can front run because it needs to be signed to make sure that nobody else from outside of this conversation can actually query these messages. And finally, there is a hash-based cache. Remember, that's to be able to find the public keys based on the user ID. So you just publish your static public keys, and they will be automatically indexed by their hash, which is the user ID. And that's how people, based on just the user ID, can find your public keys to be able to initiate a conversation with you. And all these things are kept only for 2 weeks by the nodes. So it's not a permanent storage. So here we're gonna dig a bit deeper into how we initiate a conversation. Let's say Alice wants to initiate a conversation with Bob. So Alice knows Bob's public key, especially the post-quantum MLKEM public key. And Alice also knows her secret keys. So the way it works is that Alice starts by generating something called an announcement, which contains some freshly regenerated randomness. She also encapsulates Bob's static public key to generate a shared secret, which is here, KEMSS. And this shared secret is going to be used as a precursor of the cipher key that's going to encrypt this message. So Bob, on his side, also has this shared secret just by what we call decapsulating this ciphertext that's inside the message here. This secret, together with the randomness, and Bob's public key, are fed to a key derivation function. Basically, it's a big hash that hashes all that together and generates the next key. So that's going to be used for chaining messages together to generate a new key at every message while chaining the messages together. We'll see it later. To generate an authentication key that's going to be used to derive basically the secrets that's going to be used to sign the next message, to avoid any kind of basically front running of people stealing this index for the next message. But we'll see this later. And the most important is that it generates the cipher key, which is going to be used to encrypt the announcement, and the nonce that's used for the AES encryption that's used here. So the encryption is also post-quantum and authenticated. So from there, this cipher key and nonce I used to encrypt all the important contents of this announcement. And these contents are can be deciphered by Bob because Bob also has access to this cipher key. You see, that's the first example of plausible deniability, which means that Bob also has the secrets, the cipher keys, so they can forge messages. And the contents of this announcement of Alice are an authentication blob that proves that this announcement comes from Alice and not from somebody else. And for this, Alice uses her signature, basically, using her secret keys. And inside here, there's a payload, which is a random number to add some randomness here, a timestamp, and Alice's nickname here. We also generate on Alice's side, when she makes the announcement, she also generates a fresh KEM, so post-quantum secret and public key that's going to be used to encrypt the next message. So this is a fresh key that's not Alice's static key. So that's how Alice announces this, and then she takes this message and she publishes it directly on the counter-indexed binary blobs. So from there, Bob on his side will actually list all the counter-indexed binary blobs starting from the latest one he has seen and try to decipher them using all of this. And if he manages, it means that it's a message that's for him. And from there, he can find all the necessary tools to deduce the secret keys for all the next messages. So from there, the session is initiated. So the way it works is that Bob and Alice will keep, let's say we're on Alice's side, on Alice's point of view. Both sides are going to keep a history of the recent messages they sent to each other. And every time they're going to send a new message, they're going to attach it to the latest messages. Let's say Alice sends a message. She attaches this message as two parent messages, one which is the latest message on Alice's side and one which is the latest message on Bob's side. So, of course, the ancestry of these messages needs to be consistent. It's fine. The arrows here, the thick arrows, represent the links from the child messages to the parent messages. Each of them has two parents. And this is used as something called a double ratchet to make sure that at every message, we generate fresh keys that encrypt this message based not only on our previous keys, but also on new fresh randomness and keys generated by our partner, the person we're talking with. And by mixing and matching the two, at every message, we get completely fresh randomness. And it's created in a way that even if an attacker manages to steal one of the keys, or even the static keys of our partner, they can never read any of our messages. If let's say they break the encryption key that was used for this message, they can read that message, but they will never be able to read the previous messages nor the next ones, because every time there's going to be fresh keys. And there's still plausible deniability because both Alice and Bob know each one of these keys. They can technically forge each other's messages at every step. So that's extremely powerful, because if I'm Alice and I talk to Bob and Bob decides to leak a secret, it's fine, because there's going to be new secrets for every message. So it's going to leak only one message. And even that message, I can claim that Bob has forged it because he has the secret keys to do that. It's very powerful, but it also means that it removes a bit of integrity verification. When you talk to someone, you assume in a way that they're not going to cheat you. But if they cheat you, it's a one-on-one conversation, so it's not a big deal. Then comes the messages themselves. Once a session is established, we need to send messages. And here again, it's a bit similar to what we saw previously. There is something called the seeker. That's for the index where Bob will need to look for this message. And this seeker is deduced from from basically the previous message's temporary address based on the temporarily generated key pair. and it's signed, so nobody can steal this slot. So whenever Alice decides to send this message, Bob knows exactly where to look for it, so he doesn't have to scan all messages, and all of that in a way that doesn't allow anybody else to take this slot, because only Alice and Bob knew the secret key to be able to sign and authenticate his message. So from there, the message itself again contains randomness, contains a KEM ciphertext. For those who know, it's basically to encrypt the message so that only Bob can read it. It also contains the PK next, so it's a freshly generated key encapsulation for the next message. Remember, we generate fresh keys, we encapsulate fresh keys at every message. And that way, we're ready for the next message, and only Alice and Bob know how to decrypt it with fresh keys. And if the keys are compromised, the compromission doesn't go backward, no forward. It's only compromising that one message. And from there, we use a similar technique as before, KDF that uses the key next from the previous message, that uses the parent messages to generate randomness. So by encapsulating Bob's static key, but also the PK next of the previous Bob's message, and Alice's key next, and Bob's key next from the previous messages as well. So we combine all of this, and we obtain a shared secret. Both sides obtain this shared secret, and we send it inside the key derivation function, which is used to generate the next generation for the next messages of key next. It also generates a cipher key and a nonce to encrypt the contents of the message. In the message itself, we have the fresh randomness, the fresh keys for the next messages. We have a payload that contains the timestamp of the message to avoid replay attacks. We have the seeker for the next message. That's a secret key basically that Alice just generated and sent to Bob. And this key pair Bob knows, and Bob knows where to find the next message and authenticate it from Alice. And of course, the contents of the message. So all this is then sent to this DSA authenticated binary key value store. And nobody, even unless they know this temporary secret, nobody can occupy this space. So when Bob queries this message, either the node refuses to answer Bob, and then Bob can just change nodes, choose another node, or the node lies by sending some fake information, but Bob will know it because the signature of that data would not match this fresh secret keeper that was there. Or it will send the right value, and then Bob can just verify the signature that is correct and read the contents. And if in the case where the node sends something wrong to Bob, Bob can just change nodes. So here you see that we don't trust the nodes. We assume that the nodes are unreliable, that they lie, that they're attackers, and it still works. We don't trust the backend. So that's kind of an overview, a general overview. It's a bit technical, sorry for this, but it's important. That's how the Gossip system works in its backend. That's how it uses post-quantum encryption. It's called the double ratchet. It allows for perfect forward secrecy, post-compromise secrecy, which is even if keys are compromised, the attacker cannot decipher anything else than maybe one message. Even if Bob's static keys leak, the attacker cannot decipher anything. It's extremely powerful, and it allows for maximal security while maintaining plausible deniability. So we're quite proud of this algorithm. To our knowledge, it's one of the only ones that has all of these combined. Of course, the source code is available on our GitHub. You can find it here. We have just published the scientific paper that describes all of this in a more formal fashion on our website, usegossip.com, which is, by the way, hosted on the Massa's DWeb, so it cannot be taken down easily. And I invite you to follow us on X, on our website, on our GitHub, to look at the source code of all of this. All the source codes are available and up to date. If you are knowledgeable about cryptography, please take a look at the scientific paper on usegossip.com and leave us your feedback. This is precious to us. Of course, after we converge on the final design, using our internal audits, our tests, and your feedback, We're also going to launch third-party audits, and we're going to try to work on formal proofs as well. But that's where we are at right now. We are moving forward on the implementation, and we are, of course, ready for any of your questions. So if there is any questions, feel free to ask them now. If not, I invite you to check again our socials, to criticize our system, tell us what's wrong, tell us what's broken. We are going to fix it the best we can. Tell us if you have ideas. If you are a person that needs privacy, a person that for whom privacy is sensitive, even life-threatening, tell us what missing features you see, what kind of things you don't find in other projects. We'll add them now. It's easier now than later when the system is more mature. On our side, we're gonna continue building everything, and we'll keep you up to date. Every week, we're gonna do a little chat like this, and next week we hope to show you a more refined demo. So feel free to keep up to date with everything, and thank you for being there. And yeah, thanks to everyone. See you next time. Bye.